Okay, in this lecture, we're talking about balance and stability. So, in future lectures, we're going to go way more into detail about balance and stability and get into deeper discussions about the differences between equilibrium, balance, and stability. So, for today, I'm just barely introducing the topics and just kind of lightly touching on what each of those terms mean and what the difference is. So center of gravity is where in the system gravity is concentrated. So in a previous video, we talked about center of mass. So where we put the cardinal planes, all three cardinal planes evenly through the body, where they intersect is the center of mass. So where the average mass is of the body. So the center of gravity is at the same location as the center of mass because gravity is going to be concentrated where the mass is concentrated. So those two terms are commonly used synonymously because they are in the same location, but technically they mean two different things. Center of mass is where the mass is centered in the body, and center of gravity is where gravity is concentrated in the body. They just happen to happen at the same place. The line of gravity is an imaginary line that represents the vertical pull of gravity through the center of mass. Okay, so there's the greatest concentration of gravity happens through the center of mass. So if we just draw an imaginary line that goes vertically right through that center of mass, that represents the line of gravity. So where gravity is pulling through that center of mass. So the reason we care about that in biomechanics is because we need the center of mass to stay within the base of support, which we'll talk about in the next slide. But you can see that with this person bending forward, the center of mass is now outside of the body. It's in front of the person, but it's still on top of the base of support. So the person is still going to be able to stay upright. Now, if she leans further forward enough that the center of mass moves in front of the foot so that that line of gravity is no longer lined up with the foot, it's in front of the toes, then she's going to fall forward and have to take a step or she's going to fall. Okay, so base of support is the part of the body or system that is in contact with a supportive surface, and it includes the area in between the areas of contact. Okay, so I say supportive surface, usually it's the ground, but it could also be like you're laying on your back on a bench. So, like you're doing a bench press, you're on your back on a bench. Well, everywhere that your back is in contact with that bench and where your feet are in contact with the floor and everything in between would all be the base of support. Okay, so it's a supportive surface, not just the ground. So it's the perimeter, the outline of your feet on the ground or whatever you're standing on, and the space in between them. So you could be standing on the ground with feet together and you have a very small base of support. You could widen the stance significantly and make a much larger base of support. So it's the things in contact with the supportive surface and the space in between. Okay, so getting into equilibrium, balance, and stability. So those are very related terms that people use kind of loosely, but they don't mean the exact same thing. So we're going to just kind of touch on the differences here, and we'll get into way more depth when we touch on this subject again in the future. Okay, so equilibrium is a state in which a system is at rest or maintaining a constant velocity while in motion. Now, equilibrium, balance, and stability are all defined in different ways in different areas of science. So I just want to point out that these are the biomechanics definitions and the way we use these terms. Okay, so if a system is at rest, it's not moving, or it's maintaining a constant velocity, which is speed and direction, it's going in the same speed and direction while it's in motion, then we would say it's in equilibrium. So a system either is in equilibrium or it isn't. It can't be more or less in equilibrium. Okay, we can't increase our amount of equilibrium. It either is in equilibrium or it isn't. Okay, balance is the ability to use effort and coordination to control equilibrium. Okay, so we can use balance and coordination or sorry, we can use effort and coordination. So muscle effort and motor planning, and so all of the neurological and musculoskeletal factors that come into play to control our state of equilibrium. So again, we either have equilibrium or not, and balance is the effort and coordination that we use to control whether we have equilibrium or not. So balance is a functional skill. This can improve or decay over time, because again, it's a matter of the state and ability of the nervous system and the musculoskeletal system that allows us to have balance and control our equilibrium. So that can get better or worse over time. Stability is the resistance of a system to having its equilibrium disrupted. Okay, so this is separate from balance, meaning the ability to control equilibrium. This is a quality of the system itself, not our ability to control the system. So it's the resistance of a system, the resistance of a system to having its equilibrium disrupted. It either occurs or not, just like equilibrium. Either we have stability, a system is stable, or it's unstable. So it's the body's resistance to a change in its state of motion when faced with a disturbance. So equilibrium and stability are both qualities of a system regardless of its control, and balance is about control of the system. Okay, so imagine like you have a bowl and there's a ball sitting inside the bowl. If you tap the ball, or you flick it or whatever, you tap the ball, that is a disruption. Okay, so it was an equilibrium. It was just sitting quietly in the bowl. That's equilibrium. Now, if you tap it, that's a disruption to its equilibrium. So when you tap it, if it's not that big of a tap, it might just roll a little bit and it will settle back into its state of equilibrium. That means that that system, the ball in the bowl, that's the system, it was stable because it's resisting having its equilibrium disrupted. So even though there was a disruption, it returned very quickly back to its original state of equilibrium. So that's a separate thing from any kind of control mechanism. There's no control mechanism happening here. It's simply that the system is designed in such a way that it's resisting losing its equilibrium when there's a disruption. So it either is stable or it isn't. Now, if you think about a ball, like if we flip the bowl upside down and let's say it's round on top of the bowl now because it's upside down, and we put the ball on top, it might be in a state of equilibrium. It might be at rest and not moving. But now if I give the same tap to that ball, it'll roll away and off the table and off it goes. That was a totally unstable system. There was no stability because it had no resistance to the disruption. Okay, so a system either is stable or not stable, and it's either in equilibrium or it's not in equilibrium. And balance is our effort and coordination that we can use to control our equilibrium. Now, when we say, well, can't something be more or less stable? Kind of. Really, it's either stable or not. It can just be more robust to disturbances. So like there's a difference between if I just tap the ball versus if I give it a big swat and the ball goes flying off the table, and the ball and the bowl, So, stability in that context is relative, just like I've said many times about a lot of these terms. It's all relative to the context and the situation. So in that case, that ball was stable because if I just tapped it, it would return back to its original position and state of equilibrium. But it wasn't very robust, meaning that it wasn't stable against a very large disturbance. Okay, so we'll get into that more, and we'll talk about the differences between those terms and all that in future lectures. But just starting to introduce that here. Okay, and then we have linear stability and angular stability. That's referring to the direction of movement or the type of movement in which a system is stable. So linear stability, the resistance to acceleration or change in direction. Angular stability, resistance to acceleration of rotation or change of rotation from one axis to another. So I included this picture here because this is an example where we lost stability. So maybe the car was driving in a straight line, that would be linear stability. So resistance to acceleration or change in direction. But as we all know, living in Minnesota, we might hit a patch of ice, or we're driving in these wintry conditions, and even though we're driving straight, we might not have linear stability because it takes very little. It could be as little disturbance, like hitting a little bit of ice or some thick snow or something. And now we have a change in acceleration and direction, and you end up, on the side of the road facing the opposite direction as traffic. So that's an example where we might have lost linear stability, or where there wasn't linear stability. Or angular stability would be you're driving down the road, you're trying to turn onto the next street, and you skid off and keep going in the opposite direction. You do not have angular stability in that case, because angular stability would mean you turn and the car goes where you direct it. So the resistance to acceleration or acceleration of rotation or change to a different axis. So where you kind of lose control, and hop from one place to another. So if I'm turning the car and instead skid forward, I've changed now to a different axis of rotation from the original one. So I lost my angular stability. Okay, so that is all I have for you there. Hopefully that made sense. And even if it didn't, again, I keep saying this, but we will talk more in depth about those three terms and make sure everyone is crystal clear on it in the future. Okay, bye.